Thanks, Basile. That was a very nice seminar. So if anyone has any questions, then I guess the clearest thing to do is to raise your hand in the participants list. Well, actually in the, what is it called? The reactions button. Yeah, the button at the bottom, there's a raise hand. Oh, Chris, you had a question?
Yeah. Can you hear me? Yes. Am I? Okay. I just had a question. You didn't talk much about whether the viscous dissipation was in the boundary layers or in the bulk. Yeah. I mean, usually this is the crucial thing, isn't it, for determining what the scaling is. I mean, there's usually a transition, isn't there, when you go from the situation where the dissipation is primarily in the boundary layers and when it's in the viscous boundary layers and when it's primarily in the bulk. And that's usually associated with the Prandtl number. So I mean, it sort of all ties up with what you were saying, because at high Prandtl number, the dissipation is usually mostly in the viscous boundary layers, isn't it? And at low Prandtl number, it's in the bulk. Mm-hmm. So you get two different scaling laws because of that transition, which I suspect is equivalent to what you said. But I mean, I'm just surprised you didn't put it in those terms.
I see. So I guess the first part to the answer is I don't recall having looked at the dissipation in these two regions separately. So indeed, we should do that. Then I believe for a given Prandtl number, I'm still convinced that provided you can reach large enough Reynolds number, which of course is really hard to do at large Prandtl number, you should still enter a regime where the dissipation is mostly in the bulk. Of course, if you have large Prandtl number, it might be some extremely large values of the Reynolds number.
You know,
sure. That might be part of the reason we're seeing that curvature in the data. You know, maybe we're not quite. We've kind of.
I mean, it's just that, I mean, these are the sort of Grossman-Losey type arguments, you know, and I mean, I'm just wondering how all that fits in with what you were saying in this problem. I know that they, of course, looked at the standard Rayleigh-Baynard problem where it's heated from below, but I'm sure it can be adapted to your situation.
It can probably be, although, you know, most of that phenomenology is putting a strong emphasis on the boundary layers, which we're really trying to bypass. So, you know, it's still true that some of the dissipation could take place in the boundary layers, and that might change some of the scalings of the velocity field, for instance. So what we've done, you know, we've measured the velocity field and we've checked, for instance, that providing the system is driven in a you know, high enough turbulent fashion, you know, the energy dissipation scales as U cubed divided by H, which is, you know, dissipation in the bulk. So that's something we've checked both in the experiment and in the numerical simulations.
I'm sure it'll all work out the same. it's just another way of sort of thinking about it. And
sure. No, that's a good point.
Okay, thanks. That's it.
Thank you.
Steve, you have a question?
Yeah, thanks, Basile. Very nice talk. I guess my question is related to Chris's. It's very disconcerting that what you might naively think of as a low Prandtl number fluid behaves like a high Prandtl number fluid. So, you know, you said, was it 0.02, which I would naively have thought was kind of a low Prandtl number, is behaving a bit like a high Prandtl number. So, you know, can you explain why that is? I mean, interestingly, in dynamos, what you might naively think of as a low magnetic Prandtl number also seems to behave as a high magnetic Prandtl number. So I'm just wondering if you can physically say why that's happening. And it may be related to what Chris is saying about where the dissipation is.
Yeah, you're most likely right that this is related to where the dissipation takes place. You know, all I can say is, well, that's not much of an answer, but, you know, once you've diagnosed this prefactor here and this prefactor here, you cannot do much except then, you know, extrapolate these two and see where they intersect. And you get to low values. So that's all I've done. You know, I've said, well, I was confused. You know, why is it so low? I was expecting that, you know, maybe we'd use liquid metal and we would be deep into the low Prandtl number regime, and we're not quite in that regime. So now the answer is, I don't quite know. Maybe it's just the prefactors here, you know, which are such that when you extrapolate them, you reach low values of, you know, you expect values to be of the order of 1. And
Yeah.
sometimes you're not very lucky, and order of 1 is 0.03.
Yeah, but yeah, so these are the numerical experiments, aren't they? So it should be
That's right.
fairly straightforward to look and see why it's behaving the way it is. Yeah, it's really interesting. Yeah, thanks.
Just a comment related to that before I allow David to ask his question. Does it depend on the form of the heating that you use? I guess where the, because presumably it could do, I guess the value of the Prandtl number transition could depend on the spatial structure of the heating.
That
I guess
could very well. And in fact, you know, we've read your paper, and something interesting that's very different between your study and ours is that you've conveniently chosen a forcing function, an internal heating and cooling that vanishes at the boundaries.
Yep.
And in fact, that's very useful because it allows you to, you know, to forget about any of those boundary layer corrections, you know, and that's not the focus of your study, and you're then focusing on what happens for the temperature field in the bulk. But that's something, you know, that could be desirable in an experiment like that, to have a heat source and heat sinks that vanish at the boundaries, and we would avoid all that mess. But then you know, you could also wonder.
Do you think if you did an experiment of that, you wouldn't have the same transition if you had something where you had the heat source that vanished at the boundaries?
That's right. So if we had a heat source that vanishes at the boundaries, you know, I would even suspect that we would never have the Prandtl to the 1/6 behavior here. But you know, if you think about, let's say, frozen lakes, which I've shown, you do have a non-zero heating at a solid boundary, which is this layer of ice. If you look at stars, for instance, you have no solid boundaries near the heat source, so that would be different. So maybe, you know, maybe the two cases could be relevant to different situations. But you're right, if the heating vanished at the boundary, like you did, I suspect that you would not get this Prandtl to the 1/6 scaling for the Nusselt number.
Okay, interesting. Yeah, I haven't looked at no slip actually in that case, but so I couldn't comment on that. But actually, that's interesting. David, thanks. David, do you have a question?
Yeah, I just wondered, I suppose in reality, the Prandtl number is temperature dependent, but that presumably is very small effect in your experiments. I mean, your experiment's getting hotter and hotter, and so the Prandtl number is,
That's right.
I don't even know about Prandtl number and temperature dependence, except that there is one. I know that much.
That's right. That's right. There is one. So yeah, I try to claim that reality is our lab experiment. And so yeah, there is some dependence of the Prandtl number, which is not so weak. In fact, I think the Prandtl number, you know, for water, I don't know, around 5 Celsius. Well, this is recorded, so I should be careful, but maybe it's close to 10. If you go to maybe 50 Celsius, it might drop to 3 or 4, something like that. So it's typically around 7 for room temperature. And in fact, at some point, you know, so we don't have AC inside the room, so you know there is a slight variation in room temperature between the different data points. And we check that if we include this slight variation in Prandtl number, which is typically, you know, between 6 and 7, this leads to a slightly better collapse of the data, but this remains quite negligible. We've tried to change the Prandtl number quite dramatically by going from very low temperature to very large temperature. But what happens then is that you're dominated by the, you know, the thermal leaks in the experiment and just heat coming in from the room or going out from the tank.
Okay, but in your example of ice-covered lakes, I suppose that could matter quite a lot.
Yes, that could matter quite a lot. Yeah, so then, yeah, I've been careful to avoid, you know, when I described the values of the Prandtl number, I was avoiding the region below 4 Celsius, whether this inversion for temperature, and I'm not sure how the Prandtl number behaves around there. It's even larger values, and also I think the variation is faster, closer to 0 Celsius. So yeah, the effect would be stronger probably in that case of the lake. You're right.
Okay, thank you.